Welcome back, everybody. We continue this morning with more talks on astrophysics, and the first talk will be given by E Blackman from the University of Rochester on coupling the origin and function of large-scale fields in stars.
So this is a little bit about both disks and stars, and so the main motivation is that often the origin of magnetic fields and their function are studied by separate communities. Dynamo field origin, but the output of the magnetic field, the dynamical consequences, X-ray emission, jets, those kinds of things are often separately studied, but in fact they're really coupled. And so this sort of leads into general thought about the approaches to these kinds of problems. And I think of three. One is focus on the physics of the underlying mechanisms that can be studied in detail. Lots of that is what we see here. Kitchen sink simulations, we also see that. So this would be like a shearing box simulation or a Rayleigh-Bernard convection simulation. This might be an attempt to do the solar dynamo in the largest possible spherical wedge that you could use, or shell. And then C is more of a holistic, broader, physically motivated, fast and loose kind of approach for gaining some broader phenomenological scope. And I want to sort of emphasize the importance of this one. And I think that there's a lot of opportunity to really, in both accretion disks and stellar magnetism theory, to connect the lessons from A and B into C. There's a very much opportunity to do that. It's easy to get caught up in this and this without taking the lessons learned and putting it into C. So two examples of this, and I'm going to just talk accretion disks and give a few grand challenges along this general theme. And then I want to give a kind of example of an attempt to do this kind of a holistic phenomenological model that uses input physics, each of which needs to be studied in more detail. And as a self-affirming thing, I like to say one can wear different hats. Sometimes you focus on the detailed physics, but then sometimes you sort of suspend your disbelief and try to push things forward and identify questions that this. So just there's some big picture points about accretion disks. So the spectrum modelers, when they take accretion disk modeling, they're always using 1973 Shakura-Sanayev disk model, and then they patch together other components empirically. A disk component will be calculated by, say, the Shakura-Sanayev model, but then the corona, which is X-ray emission, say, above the disk, will be patched on, not computed dynamically from a model from first principles, nor would the jet that comes from the system be computed from first principles, but sort of patched on. And the transport that's used in these models is a metaphor. It's a local viscosity, and that's of course been a problem. What is the actual mechanism? Now there's been progress in identifying various transport mechanisms, most prominently the MRI. And there are others that involve, the lessons learned from this large body of work has not yet fed back into textbook generalizations of basic accretion disk theory. These have been used as a metaphor to just give the value of this viscosity, but the transport, there's evidence that the transport isn't actually really a viscosity. And in particular, there's evidence for large-scale, system-scale, or non-local transport, sort of lots of references to say this. One is directly the observations. You see jets, you see corona. It's clearly not all viscous transport locally in the disk. So determining that fraction from first principles is an enterprise of coupling the physics here back into a kind of a textbook generalization that includes that. It's also the case that even within simulations, there's evidence that the transport in, say, MRI simulations is not itself a viscosity, but it involves stresses from large-scale fields or system-scale fields within that structure. And there are, and And one specific example is that the stresses don't scale linearly with the shear, as which would be predicted by the. And so, just to see the limitations of this kind of formalism in a very explicit sort of way, if you look at the stresses in the angular momentum, transport stresses, the standard Sakura-Tsarnaev, so this is a mean field theory approach to the stresses. You break the flows into fluctuation components and mean components, and then you see where the standard, what the standard SS73 is doing. The stress, so the VA is an alphane speed, so it's basically magnetic stress. So the full stress for transport of angular momentum, radial phi component and vertical component, has all of these terms in it. This term is the kind of accretion itself term. This is the term which transports the angular momentum from fluctuations. This thing in Shakura-Tsarnaev approach is replaced by the viscosity, and all the rest of everything else is basically ignored. So there's an opportunity to include more of these terms and think through carefully. Now, that's not to say that there's been zero work in studying large-scale transport, but it hasn't percolated into the same level of standardness that the alpha Shakura-Tsarnaev model has in the astrophysical community. And often if you go to modeling, so if you all the accretion disk studies, if you then talk to a modeler, they go back to their office and just plug in alpha. I mean, they'll may go to a conference and learn about the detailed mechanism of accretion disk, but in today's world, they still go back to their computer and just put in an alpha viscosity. So it's kind of that's a grand challenge, I think, to develop a next generation kind of mean field theory for accretion disks that incorporates this feedback from what's learned from simulations. Now, an even broader challenge is if we think of accretion disks, there's many types of accretion disks, just like there's many types of stars. And stellar evolution faced a similar problem, although much simpler because it's spherical and pressure supported and such. But we have the HR diagram for stars, which is a beautiful synthesis of all of stellar evolution that has emerged over the years. And one can envision truly the day we truly understand accretion disks that we have a similar diagram. It won't be a luminosity temperature, but it might be a luminosity hardness. And there exist such phenomenological interpretations of microquasars, which evolve on fast timescales, observable timescales. They go through state changes on days, weeks, months, and there's phenomenology associated with how the system, as a function of a single parameter, accretion rate, evolves to a high soft state and a low luminosity hard state. So it transitions between these thin disk and corona and thick disk states. I won't sort of get into the details of this, but there is a phenomenology associated with microquasars. You could imagine that the time evolution of accretion disks ultimately develops a similar diagram to the HR diagram for stars. So those are two broad challenges. Now, I want to talk now about a holistic stellar activity model, which fits into this theme of trying to push forward the kind of phenomenological scenario to go back later and think about the detailed physics. So stellar activity is magnetic activity, and as we saw yesterday, it evolves with stellar age, and I'll talk about that a bit more. But activity has a broader relevance. There's lots of interest in understanding activity, not for its own sake, in the way it evolves with stellar age and rotation, but also because there's interest in aging stars that are not in clusters, where you don't have other stars to do color aging. You can do gyrochronology aging. So there's a lot of long story to this. And also, the science of habitability is important. Young stars, if they have much stronger winds or X-ray emission, influences the atmospheres of their neighboring planets. And that's not presently really included in great detail when people talk about habitable zones. So habitable zones have not yet really coupled the role of the magnetic wind in the definition of what it actually is a habitable zone. So just focusing on sort of stars that are in this range, FGKM, sort of solar-like stars, there's an evolution of X-ray activity versus rotation that looks something like this. Saturates, I'll come back to this in a moment, but this is the X-ray activity, this is Rossby number, with all the caveats about how this is defined. The correlation time here is defined, or the convection time is defined by mixing length stellar models that match the color index of the actual stars, which is another subtlety. But there's that sort of curve. That's already an interesting curve. Yeah, so this is the more explicit. The sun is somewhere over here. What explains this kind of saturation? The saturation that Metcalf was talking about yesterday is at older ages, this thing tends not to fit this line, but tends to go a little bit out over here. There's a few other observations. So there are a lot of other observations. This is now sort of thinking holistically about a lot of observations. There's a magnetic X-ray activity, magnetic flux. So X-ray activity, linking X-ray activity to magnetic flux of a range of different objects. There are age versus rotation. I want to give, these are for stars that are from 10 to the 8th years to the present age of the sun. But a lot of the data are not, this is not precision science. So what you have in the data are relations from there's also mass loss rate versus X-ray flux. Literally, of all the stars we know, there may be 10 objects that have their mass loss rates measured. It's very difficult to do. So there's scalings that emerge in the literature for various quantities. X-ray luminosity versus coronal inferred temperature, and magnetic field versus age. You see the data are not precise, but there are trends. The Skumanich law for the rotation period breaks down at early times also. Now, there's a sort of set of trends that are X-ray luminosity versus Rossby number, X-ray versus temperature, mass loss rate was actually the best values that you can infer in this sort of broad phenomenological overview of all this kind of data. And the question is, given the level of imprecision of the data, can one come up with kind of a holistic model to kind of explain these trends? So the approach that I'm going to describe is a coupled set of equations, very simple, but involves this kind of modular approach. Dynamo, a model for the dynamo with saturation that feeds magnetic flux to the corona via buoyancy. The energy to the corona then is divided into some combination of X-rays, conduction, and wind power. So this is sourced by magnetic energy. And to explain the relative fraction going into these three, use a sort of simple coronal equilibrium model. And then the wind, the part that goes into the wind, spins down the star, and then that feeds back into the dynamo. So you can couple all this together and then make predictions for sort of all these quantities with some physical ingredients that are important. So that's this description of this kind of model. The first thing is coronal equilibrium to establish when the magnetic energy input from below is supplied to the corona, what the relative fraction is. What you do, you extremize the system in equilibrium, set up an equilibrium, and find the equilibrium pressure, and you have the input physics for conduction, wind loss, and radiation in X-rays. And one thing you find is you do this, and you can calculate the wind to X-ray, everything normalized to the sun. The earlier systems are hotter. They appear in this region. So one of the immediate things that comes out of this is that the X-ray luminosity and the wind power are very closely locked, which is observed in the sun. So that's kind of a prediction. But then at older stars, one thing is that the conduction luminosity is more important, and that takes power out of the wind, and it's one possible explanation for why, other than what was said yesterday as to why the winds extract less angular momentum for older stars. That's sort of an output of this model that was unexpected, but I'm going to focus now on the region 2 here. So we can, just the simple coronal equilibrium model, very simple. semi-analytical, does well to predict the coronal temperature as a function of X-ray luminosity. That comes out of this model is not okay. Now, the thing is, so to understand this part of the saturation curve, and we are going to use a dynamo theory, but it's important to understand this Rossby number. This Rossby number is inferred from theory, from mixing length theory, but in fact, it's from stellar models and such. It's not an observation. This is a model. This is an observation. The rotation rate is an observation. It's often assumed that the correlation time that goes into dynamos is equal to the eddy time, which is the convection time is equal to the eddy turnover time, and that the convection time from the stellar models is what you use in the dynamo theory. But in fact, for fast rotators, this isn't likely the case, and we need a prescription for this, but a physical motivation for imposing a scaling is the following. If you imagine that there's high rotation or there's lots of shear, when what would otherwise be a naturally convecting eddy has its own convective lifetime, but for fast rotators, or for shear, very high shear, that's going to shred the eddy, or the scale of the eddy is going to be reduced compared to what it would naturally be for a purely isotropic, for a purely non-rotator. So you can imagine that in the limit that the very fast rotators are very high shear, that the correct correlation time is more close to the rotation time in the limit of fast rotators, and the usual convection time for slow rotators. So you can think about how that might scale, and we use a kind of a prescription for that. This is something that real input physics is needed, but you can sort of motivate this to make some progress. So that's one ingredient. The adjustment of the Rossby of the convection correlation time that enters the dynamo theory from that in principle. The other is that the classic dynamo pictures that you see about generating magnetic fields these pictures don't conserve magnetic helicity because the field is drawn as a line. So why is this relevant? So this is now this long story behind the incorporation of helicity conservation into this kind of basic paradigm, but if you replace the field, the line by a ribbon, then you can start to begin to see how a saturation paradigm might work. As you twist the ribbon, you build up small-scale helicity. So you twist this loop, make a large-scale loop, typical alpha thing. But as you do this, you can't get this has a net. There's a helicity associated with the large-scale field here that came for free. If it was initially a loop, you've generated some helicity when you average around this loop. So the small-scale helicity to conserve the overall magnetic helicity comes in from twist. That makes the field lines harder to bend, and that's a kind of prescription which has been worked out over the years for a principle of saturation of the dynamo. And it makes a prediction that when you inject helicity into to each hemisphere, that both signs should actually appear. You can try to test whether that's true. It seems that there's some evidence. So this is just another version of that. Instead of thinking of the field line as a line, it's a ribbon, and you get these twists for the alpha squared. Now, and there's some evidence that, I always say this one is kind of interesting evidence, that there's both signs in each hemisphere, and that the scales of the different signs are different. So that's a sort of conceptual concept. So if you update the sort of minimalist dynamo to include all of these ingredients, which includes a helicity conservation, very, very minimalist. It includes a sort of loss for buoyancy or advection of helicity flux. One of the principles of this is that unless you advect the helicity flux through, say, coronal mass ejections, the field would be locked up, and the dynamo cycle period would slow down. So you couple the need to get stuff out into the corona with the dynamo itself, and then the emission that you see is kind of a consequence of releasing the helicity and the energy associated with that in the corona. Putting that together, you can kind of augment what's the most sort of a very minimalist dynamo. It doesn't have any of those ingredients into a minimalist dynamo that does, and in the part of the alpha effect, the helical twist, you replace this eddy time with this prescribed eddy time that includes the effect of the rotational on the convection, a prescription for that. So those are the sort of gradients. You can estimate the saturation either for sort of alpha squared or alpha omega, and the key is that it's weakly sensitive to Rossby number when you put it all together. So you can estimate the field by when this. So there's two estimates of this, and just put this together. And in the interest of time, I'll just say if it's an alpha omega dynamo, you get a toroidal field that's amplified above. So sorry, the toroidal field is estimated by just the condition that the current helicity approximately saturates the kinetic helicity, and that gives you an estimate for the toroidal field. The toroidal field, if it's alpha omega and there's shear, the toroidal field is amplified beyond that on a buoyancy loss time in this picture. But the upshot is that there's a weak dependence, a plausibly weak dependence that emerges from this scaling for both. For keeping these ingredients. So 5 minutes, okay, yeah. So you combine that into an expression for the X-ray luminosity, and it gives you an X-ray luminosity that depends also on the Rossby number. And it depends, and there's a parameter here which is the spot covering fraction as a function of the luminosity. It turns out that one of the results of this is that the thermal conduction to match in this simple model, so let me put all the equations that were then coupled together and I'll come together. So this equation comes out of relating the coronal equilibrium that I described first and a radial Parker wind for the wind model. That gives an expression for Lx and mass loss rate. The rotating convection business and the dynamo saturation is what I just described, couples that X-ray luminosity into the Rossby number as such. We then include a secular evolution of the angular momentum of a long time scales by a kind of Weber-Davis model, and then solve all of these together, and you can produce various solutions. So this is the X-ray luminosity versus the Rossby number, but also you can get the time evolution of all these quantities. X-ray luminosity, magnetic field. And the upshot of this very simple semi-electric model is that when you look at the precision of the data, the trends are captured. So there's lots of details, but there's ingredients here which captures a lot of the trends. And in particular, for example, the approximate Skumanich region is captured, but at early times, there's the spin down is exponential, and so it's very sensitive to the actual temperature at the coronal temperature at the sun. So if you change the equilibrium temperature at solar age, you can start with a large range of initial values of the X-ray luminosity and rotation rate and converge down to the Skumanich law later. So you can also ultimately combine all this, if you really want to put all this together and push things forward, try to make some statements about the standoff distance of the magnetopause, which relates to habitability. So, and there's also models of the more detailed models of the winds, evolution of stellar winds, much more detailed models that that I've used in a different paper to try to combine with even meteorite measurements from a colleague to compute a standoff distance as a function of age. This is the Earth's dipole moment, and the best fit data for the Earth's evolution is through this curve. And you do similar models with this more phenomenological toy model. It ends up being quite similar. And what you can and the way you would use these kind of diagrams is to say if you have an atmospheric model that tells you at what standoff distance the exobase exceeds the magnetopause, that's a scale at which your atmosphere could be blown off. So you want to know what the evolution of the wind, the magnetopause is as a function of age or as a function of different types of planets, and then you want to know how the wind evolves and what the influence on that scale is. Of course, the wind pressure against the magnetic pressure of the planet determines where that standoff distance is, and then you want to compare that to the exobase, where ablation from X-ray luminosity, also from activity, blows the atmosphere either above the magnetopause, in which case you can lose that atmosphere. And so this is a region, combining all this together, sort of a region where atmospheric models will risk blowing off the nitrogen-based atmosphere and threaten kind of habitability in that region. So that's meant to be just an example of how to push all of this forward, try to come up with a holistic model that includes various ingredients that captures general trends and has some implications. And then each pieces of those physics can be augmented with clearly further, much more detailed approach. So just the conclusions here. So accretion theory, it's a meaningful challenge to overall incorporate lessons learned from decades of simulations to revising textbook practical theory. And it's kind of an example of pushing things forward and doing this kind of phenomenological model. I created this model for the evolution of coronal activity and tried to capture some of the observational trends with a sort of simplified model that takes ingredients, pieces of physics, each of which need to be investigated in more detail and kind of in modules, and while still trying to maintain practicality. So that's kind of that's the bottom line.
Questions, please?
On one of your earlier slides, you expressed the X-ray luminosity as a function of omega and explicitly time as well. Does it depend on time other than through omega?
In this case, no, right. In this case, it doesn't, no. So in this case, right, it's, so the two time scales, so one of the simplifications in this treatment is that, it's things like a cycle period happening on a month, whatever time scales, we know 11-year time scales, but the secular evolution is on millions of year time scales. So in a first pass, I just consider that part of, the average saturation for the dynamo, and then only the average is changing over long secular times. So an important augmentation of this is to couple the sort of fully time-dependent dynamo cycle period into the secular evolution. Not that difficult to do. I have a student that's sort of working on that, but to explain the precision level of a lot of these trends over the lifetime of the star. I'm thinking averaging over the cycle period and getting a simple single value for each star. So, there is the coupling. In reality, that's a very next step of coupling the short-term time dependence of the dynamo model into the long-term secular dependence. And that would allow, of course, predicting things like the cycle period age or cycle period rotation relations, which can be also done. That's another observation.
And you could also include episodic bursts of mass loss through coronal mass ejections and things like that as well.
Yeah, that's an even higher order. Exactly, you could, so, yeah.
Other questions? Yes, please.
So are there ways to compare these predictions of yours with simulations, or are simulations not anywhere near close enough to what you're trying to model here?
Yeah, so it's an interesting question. It would be, so the yes and no. In a way, the problem is, so the issue is that, so what you're looking at observationally, is a long-term evolution of a lot of detailed physics that's going on. You have the dynamo physics, you have the rotator physics, you have the wind physics that goes into dynamo coming up, or alpha and waves that are accelerating the wind, et cetera, et cetera. So, to do a fully detailed simulation, you're asking, one would like to, have all these processes built in as kind of an experiment. But pieces of it you can study. So, if we take a part of it and say that, okay, the dynamo saturation model is this component, well, you can you can augment and feed back that module of the theory with simulations of the dynamo part of that. If that's what you mean.
Have you done that?
I mean, so the principles that have gone into the dynamo saturation part of this, you know, are the output of feedback between thinking about toy models of thinking about, you know, how dynamos saturate. And over the past decade or so, there's been I've been involved in analytic theory, and there's been simulations of how magnetic helicity quenches the dynamo. And so the scaling relations and the principles of how to include that are all sort of coupled in that piece, for example. I mean, there's still a lot more to do, but you know, trying to extract that principle from that set of comparison of theory and simulations goes into that kind of part of the module.
Thank you. There's one more question, but we can swap the computers. And
Yeah, I was a little bit surprised to see that it's hard to measure mass loss rates from coronal winds, obviously. There's very few methods that are direct measurements of mass loss. And you talked about this correlation between X-rays and wind mass loss flux. But normally the dominant source of X-rays in the solar corona are in closed field regions. So it strikes me that and in some sense, of course, most of the mass is coming from coronal holes, which are very X-ray dark. So I'm really surprised to learn your claim, or I'm surprised about it, and I'd like to understand a little bit better about how it ends up being that there is a direct correlation between X-rays and mass loss rate.
And there's some technical we can talk about there, but the way that emerges is basically, it's an interesting thing, and there's some subtlety in physics there. So we take a coronal model. I have a term that's thermal conduction, X-ray luminosity, which is taken as the specific input forms of those things for the relevant temperature regimes, and then the mass loss from a kind of Parker wind, and you set that in equilibrium. You say that in one scale height the base is in equilibrium, and you extremize that for the equilibrium pressure. And when you extremize that for the equilibrium pressure, you can then get an explicit relation between the Lx and the mass loss rate. Now, one thing that's important in that calculation is that in order to match, so this is all normalized to the sun as a data point, and to match the solar data point, we know that if we just take the naked thermal conduction over the whole volume, it doesn't work. And what we interpret is that you need to geometrically reduce the thermal conduction by just a factor of 10, and that matches all the, and that leads to this prediction. The reduction of the thermal conduction can be interpreted as a geometric effect from anisotropic conduction along field lines. So if there's a magnetic canopy in the coronal layer, the conduction only operates along, along the field and not against it. So if the spot covering fraction, or if the link from the X-ray region to the base goes through a point that goes through tubes that cover only a certain area fraction, that gives a natural geometric reduction in the thermal conduction. So it comes from that balance equation. And
thank you very much. The next talk will be given by John Hawley about stability properties of differentially rotating flows in astrophysical disks.
Really, really embarrassing if you're wearing one of these and you step out to use the bathroom and you forget. All right, so I'm going to focus on some very basic properties of accretion systems, with the notion that for an audience like this, who's working on many different types of systems, the basic physics is going to be the most widely applicable and of greatest interest. So the disk is, of course, a very fundamental structure. The universe has a lot of structure in it. Gravity is mostly responsible for that structure. If you have gravity without spin, then you end up with a sphere. If you have gravity with spin, you end up with a disk. And And so here we see disks in the form of galaxies, disks in binary systems, and disks forming protostars. The fundamental question related to accretion disks is basically, why do they accrete? One of the first disk models that sort of emerged was as a result of observing that the ecliptic was more or less a plane. Laplace postulated the nebular hypothesis for the formation of the star, the sun, and his idea did not gain much acceptance because people didn't see how you could get rid of the angular momentum. And so the disk would just sit there and would never collapse to form the sun. So instead they went with a much more plausible model of having a very close pass of another star which would rip bits of the sun out and cause that to form the planets. So that was satire, just like Donald. Anyway, the angular momentum transport then is the key dynamical question for our disks. And that is key to understanding their evolution and structure. Another aspect of astrophysical disks that is particularly showy is the fact that they form jets. And the interesting thing about jets is that they seem to be ubiquitous. Here's a list of the various types of systems that produce these collimated high-energy outflows. And so the sort of the observational notion that arises is that the combination of spin and gravity and then the additional factor of magnetic fields quite generally leads to collimated outflows. And this is the sort of the typical artist's conception of the idea. In the case of black holes, the magnetic fields become connected to the black hole, rotating black hole, and can extract basically considerable amounts of energy from the rotating black hole so that you can power a jet even with minimal accretion. I'll just mention that I'm not going to talk about jets in any detail today, but we have been able to produce jets through global simulations. The requirement is to have basically a dipole field that is deposited onto the black hole. And so it's sort of a rather special condition, and one of the key questions is the circumstances under which you can get a dipole field deposited on the black hole. All right, so focusing on transport in disks then, over the years many mechanisms have been proposed to explain how angular momentum is transported through a disk. One way is through external torques. In particular, if you did have a significant magnetic field that could drive a wind, then that wind could spin down the disk and allow it for accretion. In the case of a binary system, you can have strong tides, which can produce torques in the disk and transfer angular momentum from the disk into the binary system. In the case of internal torques, of course, viscosity is the normal way that you would have angular momentum transported. But in the case of systems like this, the Reynolds number is simply too huge, and the reason that it is huge is because the systems are huge. You're talking about solar system scale disks with very high velocities, orbital velocities, and if it's around a black hole, the orbital velocities are close to the speed of light. And so molecular viscosity simply doesn't have a chance. From the very onset of sort of modern disk theory, which sort of dates to the 40s or so with observations of systems where it's clear there was mass transfer, the realization of the combination between very high Reynolds number and shear led to the presumption that turbulence would be a natural outcome. And so if the system were turbulent, then of course the turbulent Reynolds stresses could do the job of angular momentum transport. So there was a presumption then that basically turbulence would take care of things even if we didn't know the details. Global waves is another possibility. I point out that, again, I mentioned this again, global waves tend to be non-local. And of course, magnetic fields, people recognize that Maxwell stresses could easily transport angular momentum, but the presumption again here was that the magnetic field would be subthermal and hence less important than whatever the hydrodynamics was doing. Now, we've already heard mention of the Shakir and Tsarnaev model. The Shakir and Tsarnaev model has a number of assumptions. One, it's time stationary. Two, it's possible to separate the vertical and radial directions, and it's axisymmetric. There's a great deal of simplifications. It's thin. And what Shakir and Tsarnaev said was that the stress, I want to say stress, not viscosity, was equal to alpha p, and alpha was simply a dimensional parameterization. If you think of this not as a function, but as a number, like a Rossby number or a Reynolds number, and call it the Shakir and Tsarnaev number, then you get closer to the spirit of what alpha really should be, the way alpha really should be thought about, is that it's a relationship between the net stress in some sort of average sense to the thermal energy. All right. I'm not going to talk much about simulations, but there's two sort of classes of simulations that people are using to approach the disk problem. One is a global simulations. Those are more challenging, of course, because of the great time and length scales involved. The other is the so-called shearing box, which is to go into the disk, take a very local region where you can ignore the curvature from the radial coordinates and map it into a Cartesian box. The box is centered on a radius that is orbiting with a frequency omega. So you have this local shear flow, and you imagine that this box is surrounded by tiles of other boxes moving at relative shear. So it's a shearing periodic system. You can do it with or without including the vertical gravity. And the advantage of this is that you can pack a lot of grid zones into your simulation and resolve the turbulence and whatever else is happening, but you don't get the sort of the global evolutionary effects because there's no net, there wouldn't be any net mass motion. Another factor of it is that if there's net fields in the box, they're generated by currents outside the box, and so that can't evolve. The equations for the shearing box are these. The interesting bits of these equations, one, here's the Coriolis term, and here's the tidal term. The shearing box can be used for different distributions of angular momentum. Of course, Isaac Newton and Johannes Kepler want us to use the Keplerian rotation law, which is omega goes as r to the minus 3/2. That is then parameterized as q. So q is 1.5 for Keplerian disk. If L is constant through the disk, then q is 2. Q equals 0 would be constant omega. And so these shearing box equations, you can set q to whatever you like it to be. But like I said, the most natural one will be the Keplerian one, of course. The shearing boxes have been approached by a large number of numerical techniques, direct finite difference simulations, flux conservative simulations, spectral methods. And so I think if we could have a very long conference on shearing boxes probably I think at this point there's probably been thousands of papers written on shearing boxes. So if you're really keen on it, you can spend some amount of time working on that. All right. A couple of days ago, we heard from Hantu the experimental result that hydrodynamic turbulence doesn't work in an accretion disk. Okay, and he had to yes, no, maybe stuff and everything. And let me just say it's no. Okay, just no. All right. So if you take anything away, just put your money on no. All right. Here are the fluctuation equations in the accretion disk. So you have the radial velocity fluctuations, the z velocity fluctuations, and the phi velocity fluctuations. Here's the epicyclic frequency. Remember that if you take a blob in a orbit and you perturb it radially, it doesn't keep going. It executes an epicyclic motion. That's sort of a little counter-rotating thing, dating back, of course, to Ptolemy, who first discovered this effect by setting epicycles onto the model. Okay, so this here is your key to hydrodynamic angular momentum transport is the non-axisymmetric pressure gradient. In the case of shearing flow like this, you could set up a wave. Could be a shock wave, for example. It will naturally be, even if it's a leading wave, it'll end up being sheared into a trailing wave. And so as a fluid element goes by, it hits that wave, transfers angular momentum into the wave, and then that fluid element loses some angular momentum. Again, the thing with a wave, of course, is that it's non-local. We don't know where the angular momentum will be deposited, but it's probably not. It's probably taken out to some large radius. In the case of, again, a binary system, the wave is basically transferring the angular momentum to the binary orbit. All right, so here's the Reynolds decomposition equations for hydrodynamic fluctuations. This is the energy in the phi component. This is the total energy here. And here is the Reynolds stress. Now, we find that a positive Reynolds stress will give you a positive contribution to the energy in the fluctuations. Up here, however, we see, again, a positive Reynolds stress. But while this is minus 1.5, this is 2. Okay, so 2 plus minus 1.5 is plus 0.5. And then there's a minus sign out here, which means that a positive Reynolds stress removes energy from the phi component of the kinetic energy. So if you basically had a situation where you had a Reynolds stress and it was extracting energy from the flow to give you a total increase in energy, you are at the same time killing off the fluctuations in the phi component, which are producing the Reynolds stress. Again, this term is the escape valve. You have that term significant. To overcome the damping effect of this term, then you can have angular momentum transport in a sustained manner. One example of an early simulation many years ago, Jim Stone and Steve Balbus did a simulation in a shearing box where they put a hot plate at the equator to drive convection. And so by having a hot plate in place, they could in fact drive turbulent motions. They were mostly vertical convective motions. In that paper, they actually saw transport of angular momentum inward. But more recent simulations with higher resolution have found some transport of angular momentum outward, again, through the creation of global trailing pressure waves. Okay. Now, if you consider changing the Q value in these simulations and going to the limit of Q equals 2, and let me just back up here and say it. At Q equals 2, this is minus 2 and this is 2. 2 plus minus 2 is equal to 1, yes. just like my classes. All right, 0. Okay, so that vanishes, and that's kind of interesting, okay, when that vanishes. Now, again, for a long time, it was assumed that some nonlinear instability would exist in shear layers that would apply then to an accretion disk. And of course, people know that in the case of a shear layer, it does go unstable for a high enough Reynolds number. Okay, it was assumed that result would carry over to disks. In the constant angular momentum case, the epicyclic frequency is 0. There's no restoring force anymore, so you push the fluid element out and it doesn't come back. Okay, and if you look at the equations, the shearing box equations, in the limit of Q equals 2, they basically are equivalent to a simple shear set of equations. Okay, so what we see in the shearing box situation is that as Q goes to 2, the frequency goes from a real positive frequency, the epicyclic frequency, to 0. And then as you go beyond that, you're going into the Rayleigh unstable limit, and omega squared becomes negative. So you just do the classic Rayleigh unstable situation. So the instability in the shear layer is, in fact, a neutral mode. The linear amplitude force is summed to 0, leaving you with the nonlinear terms to destabilize the system. In generic disks, Keplerian disks, the epicyclic motion is highly stabilizing. And so, in some sense, the behavior of shear modes is in fact special and happens at the transition between Rayleigh stable and Rayleigh unstable flows. Okay, so if you do simulations in the shearing box and you play around with the Q value, you go in there and you beat the hell out of a Keplerian disk and it just dies out. You start letting Q approach 2 and it lasts longer and longer. As you approach 2, the constant angular momentum case, basically the fluid fluctuations grow and are sustained, and if you go beyond that, then of course it's Rayleigh unstable. In this study, which was done some years ago, I featured my crudest resolution simulation that I ever did, which was 8 by 8 by 8. Okay, and the purpose was to show that in an 8 by 8 by 8 box for the Q equals 2 disk, it was unstable, and indeed it was. And so the numerical viscosity did not stabilize the system, for an 8 by 8 by 8. That was also one of the cheapest simulations I ever did. Since the Papaluzzi-Pringle instability was mentioned yesterday, I thought I'd throw this picture up. When I did, I realized that this picture comes from 30 years ago, which was personally upsetting to me. I doubt it matters much to anybody here. It's just that I hate to think I've been messing with this for 30 years. The point of it is that the local shearing stability of a Keplerian flow does not mean that hydro instabilities don't exist, but that the hydro instabilities we would be looking for would be global modes, such as the Papaluzzi-Pringle mode, where for a slender ring of gas orbiting around a central mass transitions to this counter-rotating vortex structure. I think we heard some about vortices yesterday, I believe, and I believe we may hear a little bit more about vortices today. All right, so how are magnetized fluids different? If you go back to this equation again, and now we include the magnetic fluctuations, we add the Maxwell stress, okay? So again, in the energy equation, the negative Maxwell stress just adds to the total stress and adds energy, so it taps into the differential flow, the differential rotating flow, which is the source of free energy in the system. And the key difference is up here that the Maxwell stress doesn't couple to this Coriolis term, because what the magnetic fields do actually is destroy the epicyclic motion. Okay, so it couples to the shear, but it doesn't couple to this Coriolis term. So as long as this term is bigger than the Reynolds stress by some factor, which is the difference in the Q from 2, that it now becomes a source for these fluctuations. And so the fault in the fluid hydrodynamic equations is now corrected by the magnetic field. All right, so this is to sort of demonstrate the MRI. One of these spacecraft is now obsolete. In a few years, I'm going to have to give up using this slide, even though it's both are going to be obsolete soon. Yes. Again, in orbital motion, somebody at a lower orbit goes faster than somebody at a higher orbit, even though the higher orbit has angular momentum. If we now connect the two spacecraft by a spring, the spring will tug on the lower spacecraft and tug on the higher spacecraft, and in doing so, tries to drag the space shuttle forward and pull the Hubble Space Telescope backwards. Pulling the Hubble Space Telescope backwards reduces its angular momentum, which makes it drop to a lower orbit, which makes it go faster. Okay, so the process of pulling between these two spacecraft causes them to separate at greater and greater distances and greater velocities. Okay. The analogy is exact in the local limit between the spring tension and the magnetic tension. So in the magnetorotational instability, the stability requirement is this. The wave number dotted into the alphane speed squared is greater than the background shear, omega. And this was one of the interesting little aspects about the magnetorotational instability, is that there's the magnetic field strength enters only in coupled with the wave number. And so for any magnetic field strength, you can find a wave number that's unstable, assuming that, this condition doesn't hold. That's the stability condition. The maximum growth rate for the MRI is, in a Keplerian disk, is 3/4 omega. The maximal wavelength is basically the distance that an alphane wave can travel in an orbit. Okay. So weak magnetic fields then are the ones that are more important than strong magnetic fields in this context. The growth rates look like this for a vertical field. This is KZ versus a growth rate. So the maximum is here, which occurs for KR equals 0. At the strong field limit, you get a cutoff. The cutoff is because if you go strong enough, think of your springs between the two spacecraft. If it's strong enough, basically the spring can overcome the dynamical, the orbital dynamics. It just holds the two spacecraft together. But although the growth rate shrinks as you go down to 0, it doesn't go away at close to arbitrary limit in magnetic field. There is also a toroidal field MRI. Toroidal fields are unstable to non-axisymmetric modes. In the case of non-axisymmetric modes in a shearing flow, the wave numbers are time dependent. The mode growth occurs for small values of k over kz. This is a point that should be mentioned, is that in fact the z direction is special. The vertical field tends to have the most aggressive MRI, and the vertical wave number enters in ways that aren't matched by the azimuthal or radial wave numbers. So the instability for a toroidal field favors large kz values, and for a given mode, because you sort of evolve into and out of the unstable region as the KR swings through 0, the growth time for a given mode is limited, but the growth can be very, very large. The stability limit for a toroidal field is when the alphane speed is equal to the orbital speed, which is an enormous magnetic field. Okay. So the MRI then is local, linear, independent of field strength and orientation, and is active for relatively high plasma beta values. Traditionally, people tended to think of the importance of magnetic field purely in terms of its energetics, but what we see is that magnetic fields enable modes that are not possible in hydrodynamics, so it's not just a matter of energetics. We saw this on Tuesday or Monday. Which day? Monday. It all blends together. This is an important point that Steve Balbus made, actually in Balbus 1995. The generalized Hoyland criteria for an accretion disk in hydrodynamics, this is what it looks like. And in magnetized, this is what it looks like. And the difference is that in the magnetized version, omega has replaced L everywhere. Otherwise, it's identical. Okay. There's a more general observation that was made by Steve in 2001, which I show you there, and which led to him realizing that there's something else called the magnetothermal instability, which is that, again, what we see in the MRI is that the magnetic field produces a tension force, which doesn't exist in hydrodynamics, and it's that tension force which substitutes in the stability criterion omega for L. Over here in the magnetized and unmagnetized case, there is a magnetic field can conduct heat along the magnetic field line, which is not present in just an adiabatic hydrodynamic fluid. And so the conduction of heat changes the classic stability criterion from one depending on entropy to one depending on gradients and temperature. Okay, and again, the idea is that what magnetic fields can do is provide a mechanism to tap into different gradients compared to what hydro can do. The question, which sort of follows from the previous talk, is under what circumstances can you regard MRI turbulence to be like an alpha stress, an alpha model? And the basic thing is that here are the Maxwell and Reynolds stresses, which again occur in these two equations. The key for the Shakura-Saev model is that locally, the same stress that transports angular momentum deposits the energy released as heat at that same location. Okay, so if the MRI acts locally and promptly, then it will be pretty close to an alpha-type model. But if there are non-local effects, which there's certainly evidence for that in a number of simulations and other things, non-local effects are not modeled by an alpha. Okay, so that's the thing to keep in mind. This is just a sort of an advertisement, I guess, that in the shearing box simulations, there is a dynamo observed. This has been observed by hundreds and thousands of people in millions of shearing box simulations. This one happens to come from Jake Simon, who's back there, and so you can ask him about it. But what's remarkable about this is that a later thing that Jake did using bigger and bigger boxes, this dynamo got more and more regular, and empirically, you can just model this thing perfectly as an alpha omega dynamo with an alpha equal to basically a value which gives you a cycle about every 10 orbits. That doesn't tell you anything, of course, but it just fits it perfectly. It's quite remarkable. Just a final little comment on non-ideal. If there's resistivity, the MRI will suffer because the field will slip through the fluid rather than staying fixed to the fluid. That changes the stability criteria. If there's viscosity, it doesn't change the field doesn't slip through, but it damps motions on the scales where the field might want to be acting, so that's another way it affects it. So if you, MRI tends to be suppressed for magnetic Reynolds numbers of 1, and I'll just again mention this, that simulations have shown an effect relating to the magnetic Prandtl number such that the turbulence level increases with magnetic Prandtl number. Whether this is purely a phenomenon due to the numerical simulations or it would carry over to the real astrophysical system where the viscosity and resistivity are on minuscule scales compared to what we're talking about here is an open question. Advertised for Jake Simon's talk this afternoon. He'll be talking about ambipolar diffusion and the Hall effect and their influence on the MRI. So to summarize, MRI leads to disk turbulence. The turbulence saturates at subthermal levels, and it's different if you have vertical fields or not, so there's still a lot of interesting questions there. It does the job of transporting angular momentum very well. In our studies to date, it does thermalize pretty rapidly. Big question, which is the dynamo effect. We observe this alpha omega dynamo in shearing boxes, but is that really going to, is that significant, or does it just maintain the turbulence as you go through time? And finally, non-ideal plasma is very important for protostellar and protoplanetary disks where you cannot assume that the disk is fully ionized, and you can't assume good coupling with a magnetic field. Okay.
Yep, thank you very much. Questions?
So I agree that it's difficult to extract turbulence from the shear in non-magnetized disks, but what you admit from your discussion is the fact that realistic disks have radial entropy gradients, which can be tapped to generate turbulence if you have radiative damping, as has been found by Nelson et al. For the vertical shear instability I talked about on Monday, and also for the convective overstability that Hubert Clark will talk about later today.
Sounded like a comment.
Anything else? Otherwise, I think we should. Yep.
So 2 questions. The first question is, there is no nonlinear hydrodynamic instability in the sharing box simulation. But sharing box has no curvature effect. Is it possible to recover the curvilinear terms to consider the curvature effect, for example, the Gertler vortices or Rossby waves, to study again the nonlinear hydrodynamic instability? That's the first question. And the second question is about your toroidal MRI. I still don't understand how can you exclude the possibility of the current instability, because toroidal field is associated with a poloidal current, and poloidal current will inject free energy into the system such that instability will occur in addition to the MRI. So how can you exclude this possibility? So,
Well, I don't think I was excluding anything. I was only talking about what was present, definitely. One needs to, first, in the first question, one needs to distinguish between local, a very local shearing instability versus a global mode, which is not ruled out if you have the right conditions set up for it, such as the formation of vortices or the Pavlovic-Pringle instability or anything like that. And again, in the case of current instabilities or other thermal instabilities, all sorts of other instabilities, the existence of the MRI does not preclude the existence of those other instabilities. Okay?
Okay, thank you very much. Yuri Tumri will be talking about intense core dynamos in massive B-type stars. Yuri, please.
Well, these sound like fighting words, intense, massive. What is meant by this? I'd like to talk about fairly large stars that have a high luminosity. Quite a few of them end up blowing up as supernovae. We're kind of interested in which may or may not survive to do that. And by massive, the luminosity is extremely sensitive to essentially the mass of the star. And generally, if the stars are more massive than about 8 times that of the sun, then during the longest phase of their life, which we call the main sequence, when they burn hydrogen into helium, they have a reasonable chance of blowing up. And we'd like to explore the question of what may modulate whether this occurs or not. If you think that this is a fairly abstract discussion, then please, as most of you appreciate, you are made of star stuff, and the star stuff is made by stars like these, many generations of them, of cycling. Our universe is about 13.4 billion years old. These B stars might last for 30 million years in those phases of gradual burning. Other things happen then maybe over another 10 million years, compared to the sun, which on the other hand lasts for of the order of 10,000 million years. So big changes. But it's also a subject that is largely sort of understudied, and I think it deserves study. Now, anyone who has taken an astronomy course or anything else knows about the Hertzsprung-Russell diagram, which is sort of the calling card for almost all of stellar astrophysics. It has peculiar properties that have only historical precedence, why anyone would refer to stars as an O and a B and an A and an F and a G and a K and M. And we've been using this pretty consistently throughout here. That has had to do with essentially certain properties of badly represented properties of stellar spectra, because it was thought that they should be an A and a B and a C and a D star, and Annie Jump Cannon showed us that that was all screwy. At a time when women were not allowed to be astronomers, but they were among the more competent ones at Harvard. But there's sort of a main street where we plot essentially how much energy comes out of a star in terms of solar units compared to some properties of the surface temperature of the star. And we really will be concerned here with stars on this region, this central strip where hydrogen is being burnt into helium in their cores. And then other fancy things happen also when stars blow We, of course, have spent much of this meeting talking about G-type stars, which are our sun, and various variants like that. The main issue is that the thing that controls almost everything about stellar evolution, although people who do radiative transfer think that's important too, it's really what is your nuclear burning rate and how sensitive it is to temperature. So that if you took the sun, which has a central temperature of about 16 million Kelvin, it will last for this 10,000 million years. You increase the mass of the star only by a factor of 10, and you've shrunk that burning period to about 20 million years. That's a very large factor difference. And in fact, the luminosity goes roughly like the mass to the 3.8 power or something like this. Now, with that, of course, comes a very much larger luminosity. Here it looks like it might be of the order of 6,000 or 7,000 times that of the sun for a star that might be 10 times more massive. Also, of course, where you have convection and other things occurring changes. If we look at our sun as a nuclear burning center, of course, radiation carries that out, and we finally have a convection zone as a shell. If we go to slightly more massive stars, 1.5 solar masses, we call them F-type stars. The radiative zone has expanded, the convection zone has shrunk. Eventually, by the time we get to be an A-type star, which are some of the most luminous by number, luminous stars, a large number, they're about 19 or 20 times the luminosity of the sun, 2 solar masses. They have a large radiative envelope and a convective core. The opacity of the material is high enough that you actually have to turn it over to be able to get the heat out rather than radiation only doing it. And the B-type stars that we'll be talking about, and a good example is 10 masses, so that we are beyond that magic limit of can we blow it up as a supernova, maybe have some interest in that. But at the beginning of its life, when it begins to do the nuclear burning, it has about 6,000 times that of the luminosity of the sun, and only about 4 times the radius of the sun, 10 times the mass. But what makes this into a fairly fierce beast is that its central temperature, in order to support this star, is about 32 million Kelvin, and a central density of about 9 grams per cubic centimeter. And that is sufficient to favor the CNO cycle for burning, which is much more rapacious than anything with a PP chain. And that's the game. So these massive stars have some interesting properties. And our B star in this arrangement, of course, lives here. And the type of star that we will be dealing with is a B star. Why do we bother with it? Well, in the same way that we've talked about what motivates our work. Well, certainly stars are the primary builders of magnetism in the universe. We may do other things. We can do them maybe in disks, but stars are kind of the champions. And of course, stars are not benign in simply hanging onto their mass. They tend to have winds, which influences the mass loss. So that's a fairly significant factor. And of interest, particularly to the more massive stars that we're talking about, the end state of the star may depend very sensitively on what's left when you come off the main sequence, when you've exhausted your hydrogen in the core and begin to do shell burning of various sorts. So is it that, depending on how much mass is left, you emerge as a white dwarf possibly at the end of the game, or a neutron star, or a black hole, or nothing? And nothing, it means that you really probably blast everything back into recycling. So the stars are certainly the big recyclers, and it's also quite clear that in order to have enough of the stuff out of which most of us are made, you have to go through many generations of stars. The sun cannot do it. It can do it benignly, but if it sticks around for 10 billion years, there aren't too many generations of suns. On the other hand, the B stars, if they last for 30 million years or so, 40 million years, you can chew through them fairly well. And in fact, of course, we know that anything more of higher mass than an iron has to be done in a kind of a supernova process, perhaps. So my gold ring supernova, probably quite a few of them. On the other hand, it may be also, maybe those S process reactions are not fast enough or frequent enough that we may in fact do them by neutron stars tumbling together into neutron stars and making gravitational waves and making some of this stuff also. So we're basically, astrophysics, of course, in many ways, it may be accretion disks. There, as you say, the problem is how to feed the monster. Here, it has a lot to do with how do you dispel material from these stars. And Stanowaki is really one of these major experts on massive stars and their wind losses. And he will be the ultimate speaker today. So in a way, we're interested in what is it that sort of controls a little bit whether a star becomes a supernova. This is the youngest supernova remnant in our Milky Way. And with a very long exposure, that little dot is a neutron star. I think it was about a 1,000,000-second X-ray image to be able to see it, fairly dim. Of course, rather more dramatic was the well-documented supernova, the Crab, which also has a pulsar in its middle. But both of those are core collapse supernovae. So they were massive stars that didn't lose enough stuff so they could actually collapse. So a fairly interesting topic in much of astrophysics has to do with all these sort of sensitivities. So if you might ask, well, where is hydrodynamics useful? To many people in astrophysics, it's really kind of winds, mass transfer. It's interesting. We're fascinated by the turbulent processes. And of course, what was rather charming, it took also place on the 4th of July, because the Chinese were good enough to actually know what dates were in 1054. And it's the first of the Messier object, M1, because you could actually see it with the earliest of telescopes. So we'd like to look at essentially core dynamo action in a B-type star. We build on previous work that was done really by people like Nick Featherstone on A-type stars, which are less massive, but also have core dynamos. But this character has luminosity of about 5,700, whereas the A-type star central region only had a modest 20 factor. So what we'll do is study a convective core and a good fraction of the radiative envelope, not all the way to the surface in terms of just computational efforts and resources. So we'll model the inner 65% of a B-type star, which is of 10 solar masses. We'll, out of that whole radius, 23% is a convective core, the rest is a radiative envelope. There's small ionization features with iron that give you a bit of convection just below the surface. And we'll use the code that you've heard about quite a bit already here, the ASH code. And we'll study essentially the star at 8 rotation rates from something that is very slow to something that is about 15 times solar. Now, of course, as appropriately, it was said that the path in much of astrophysics has been to model everything in sight. Of course, in a sense, it's become the third branch of astrophysics and many other subjects, because it gives you, not that it tells you the truth, but it gives you a way of thinking about it. And then you can criticize and have meetings and discuss and maybe emerge baffled. And we're also reminded that some of the things that we are modeling is not really a very slippery plasma, but maybe more like concrete. But the code that was built that could deal with full shells or the interiors of objects involves all of these players. And of course, now there are also several global other fully three-dimensional codes, including Rayleigh, that Nick Featherstone told us about. So since the kitchen sink was invoked, it is useful to have some experience with not just one model that you've worked with or star. I mean, it's useful to have perspective, and it's similarly useful to read the literature and to know what else has been done. And sometimes, of course, that's a bit of a problem when papers are written. It's as if you only cite the last 2 papers that are written and you have no responsibility for everything else. But so a lot has been done with ASH with different types of stars that are these lower mass objects. In particular, Nick Featherstone worked, and with some others, on a 2 solar mass star, which is the A star. And today I'd like to talk about essentially a 10 solar mass star and its properties. If we look at the star model domain and radius, we've sought to take the structure out of a fairly honest, or at least as honest as we know how to build stars, stellar structure and evolution model. So it's a fairly young star of 10 solar masses that has just arrived on the main sequence. And as a function of proportional radius, this star is really 4 times the radius of the sun, but we will capture its convective core, which occupies about 23% in the interior. We will put in heat at a rate which is appropriate with the nuclear burning generations. So it's realistic in that sense. So are the other opacities. And we'll bound this by a large radiative envelope, which should really go all the way to here. But we're here concentrating more on these properties. This churning that goes on in here certainly generates internal gravity waves. They have a rich behavior, even richer when the thing is rotating. But we take a temperature structure and density structure and a Brownian oscillator frequency, which in our modeling are very similar to what a stellar evolution code, MESA, would provide for the 1 million year old star. The overall luminosity in that star, total luminosity, climbs up. The MESA models will give you the dashed lines. This is what kind of goes into our models. So it's a combination of an enthalpy flux being carried by the convection, En, scale luminosity, the significant radiative component also, not sufficient to keep this from being superadiabatic, and there will be some eddy fluxes. If we put this thing together and look at one snapshot, then we're really concentrating mostly on this little region, which is the convective core, but we have also a large domain full of gravity waves, which we won't discuss much here. And the scaling is, we're looking at essentially the radial velocities as shown here, and scaling in the central core region compared to that of the much quieter outside radiative zone differs by a factor of 1,000. So our scaling on the inside for these radial velocities is 100 meter per second scaling and only a tenth of a meter in the outside. So what does this do? Well, they're vigorously active. I won't show you any movies, but I'll show you a few snapshots and talk about the characteristics. So if we currently ignore most of the computation and just kind of focus on what does the core region look like in one of our fastest rotators, we look at 8 different rotation cases. And this particular one is rotating 16 times faster than the sun. And curiously, it's also at about 15% of the breakup speed at the equator for these big envelopes. So these are fairly fast rotators. I should say the B stars seem to come in 2 classes. Ones that are rotating fairly leisurely, where their tangential velocity to the surface is about 20 kilometers per second, and others that are about 140, 180. The breakup velocity at the surface is 700. So it's a kind of bimodal distribution. One might ask, why? Presumably because you've spun some of them down. That's the storyline. And further, I mentioned magnetism, but what's the evidence for magnetism? Interesting enough, only about 7% of B stars show detectable magnetism at the surface. And one wonders why. Now, of course, most of that detection, there are challenges of, are you blurring the spectral lines, spectral polarimetric detections, but it's interesting, not that many are magnetic. On the other hand, what I'd like to show you that they all must be magnetic in their cores, and they just can hide it. So they can have a sort of quiet churning away. Theoreticians can have pleasure, but only maybe some small fraction makes it through. Because one of the problems is that that even if you build fairly strong fields, they may not be sufficiently buoyant to survive travels through a very large radiative envelope. And maybe the 7% really are more reflective of what were the primordial fields that were put together when the star was assembled. But I'll show you some other aspects from Kepler that suggest that we could actually maybe test what happens at the center of these stars. If we looked at sort of just if we looked at one snapshot of our star with the rotation axis here, and we're just kind of imaging the core, the radial velocities at the edge of that core are shown here. And their inflows are yellow, outflows are blue, and this is scaled typical velocities of the order of 100 meters per second, 200 meters per second. If we took an equatorial cut through the same thing and both drew the magnetic field lines, but colored them by the sense of the radial field, so that red is outward directed field, blue is inward, and we clip them at a modest megagauss. And that's where the fierce fields come into play. Maybe the peak fields can be 2 million Gauss or so. So, you know, it sounds like we're talking about the federal budget. It's real money, or maybe it's real fields. Maybe not. But what emerges from all of these solutions is that this fairly rapidly rotating star has essentially columnar type of vigorous, churning, evolving convection. Maybe there could be about 8, 9, 10 cylindrical type of structures, but the flux itself, magnetic field lines are able to get through the center of the core, and they mix. So it's a large churning piece of machinery. If we wanted to say, let's see a little bit more, you saw these two pictures. If we did the same magnetic field line rendering from the side in the same vantage point as this, we see that there's a fair amount of complicated threading of the fields throughout. The work itself is right now in Apogee and Press with these three authors. There's an, I think, published in any week. If we looked at the equatorial cut sampling, the entire computational domain is much larger, but if we looked at 4 samplings 20 days apart, and this star is rotating in 1.5 days, and we're in a co-rotating frame, the evolution of these circular structures is fairly slow, but quite determined, and they also go through the core. What is interesting, maybe, at least to us it is interesting, is that you've attained field levels that are substantially super equipotential. That the magnetic energy may be 10 times that of the kinetic energy. And we may very well be limited by how we handle diffusion in these systems. And of course, the appropriate question to ask is, how do you do that? I mean, how do you arrange it so that the Lorentz forces don't essentially saturate you and stop the field from getting much stronger? And so that's a central question of some interest, which I'll get to in a moment. The characteristics of what is going on if we look at this equatorial cut structure here, but look down on it, there are a lot of single convective columns. Maybe they're simpler than they would be within this actual star, but if we show essentially the flow field, magnetic field, and them combined, it's very clear that there's a complicated wrapping and unwrapping and coupling through the core that goes on. But the big question is how to, this is one of the super equipotential solutions. How do you survive the Lorentz force feedbacks? And there are really two issues that we can really see. One is that, of course, Lorentz force is V cross B. So if you want to limit some of that, try to have both the magnetic field and velocity field be almost aligned. They won't be strictly aligned. The main balance will be magnetostrophic, so it will be between Coriolis forces and Lorentz forces. But the alignment is certainly there, and we can look at the PDFs of the distribution functions, and it's very, very evident. And the other thing is, try to arrange it like you would do if you had to deal with creditors. Just move on before the bill comes. And so the game here is that you have the strongest flows slightly displaced from the strongest magnetic fields. And so if we looked at this where the magnetic energy is shown in the red tones and the kinetic energy in blue, and the overlap is in the purple and a bit of the green doesn't occupy that much of the total domain. So that although you have strong fields, very significant flows, they don't get quenched. And it may be that one might get to considerably stronger fields. When we in fact analyze the 8 rotating cases that we looked at, from fairly slow ones to fairly fast ones, it's fairly interesting that the magnetic energy changes somewhat. It climbs with faster rotation. These are the faster rotating cases. But the kinetic energy of the convection, on the other hand, decreases quite significantly, and yet it's still carrying out the luminosity. And so the ratio of magnetic to kinetic energy climbs. And it may very well be, in some of these samples, the peak fields are like 1.66 megagauss. Even the RMS fields are still really 0.2 megagauss. And we can do various scaling analyses in the same way that Peter had done for planets, and we can find that there really is a sort of fairly simple relationship that we could, in principle, invoke as we look at our 8 different rotation rates to study particularly how the magnetostrophic balance comes in. So very simplistic models are either the blue line or the dashed green line, and these are the solutions from the 8 cases that we ran. But of course, these things probably can also be influenced by whether you start from weak field initial conditions or strong field initial conditions. We can pop them into multiple ones as the Earth dynamo problem. People have learned that you could probably have some strong solutions and weaker ones. I was showing you mostly the weak initial conditions. The strong ones can build sometimes fairly large islands of very strong fields, very lumpy. Now, let me just end with just the question of, so here we're building these strong fields way inside a massive star, and are we safe from any scrutiny? Because only 7% of the stars show strong magnetism. So what's with this megagauss fields deep in the interior? Why not a gigagauss? Well, if you could build a gigagauss, those would probably erupt and make it through the surface. But an interesting thing from Kepler keeps coming up in many ways. One of them is probably some of the most fascinating discoveries, is that you've been able to see a whole bunch of red giant stars that normally you thought would be pretty boring. I mean, they're big. After stars come off the main sequence is now burning hydrogen into helium in a shell. But the main thing is that in those stars, the red giants are ones where you have a sort of a quieter remnants from all the nuclear burning in the past. You have some shell burning going on, and then a large envelope on the outside, which is a radiative envelope. And so you have the possibility of having P modes on the outside and G modes in the inside. Sorry, I got it backwards. There's a convective envelope outside and a radiative core. And so the question is it possible that the G modes and the P modes can be coupled? And they can be if their periods are very, very commensurate. And the red giants seem to be very kind in that. In particular, one finds from almost 5,000 red giants that have been observed, they're bright, they pulsate nicely, that a number of them, if you looked at their spectra, one has found that the dipole mode is suppressed in a number, maybe 20% or something like this, of the individual red giant stars. And the question is, why so? What's happened? How do you suppress it? But it's a case where you really are getting both P modes and G modes as coupled modes. And the proposition is that you're having essentially a magnetic greenhouse effect that Jim Fuller and others have written about, where you generate P modes within the convective envelope. Some will travel inwards, they will couple to this cavity, and that coupling can give you a modified frequency that you could essentially see the G modes that otherwise would not be able to tunnel through to the surface to be observed. And so you're able to sample properties in the core. And then the question is, why is it that some of these stars have missing dipole modes, where everything else is coupled? And what they're offering as a suggestion is, in fact, that what you're able to sample are fairly strong magnetic fields. If there were to be strong magnetic fields in that remnant region that at one time was a convective core, they would lead to other types of scattering and actually substantially diminish the coupling, leads to scattering of some of the G modes. And if you ask, well, how strong a field do you need to be able to accomplish this? Well, the order of 100,000, 200,000, a million Gauss. And so, interestingly enough, it's possible that with these red giants, you're sampling actually properties of what may have occurred in the core while it was convective. Now, of course, it turns out that these red giants are not the B star progenitors or companions. They're the A stars that Nick Featherstone studied, but that's fine too, because he was building fields there that are of the order of 100,000, 200,000 Gauss. But it's just interesting, the great surprises of Kepler, that you think that you're safe, but then they're able to actually start sampling, which is a great delight. So thank you very much.
Thank you. Questions, please. Yes, Eric.
Just going to ask, when you were talking about the Lorentz force, you said V cross B, and I wondered about, it shouldn't be J cross B.
Oh, J cross B.
But the alignment then was J dot B as opposed to, the alignment, the connection between the alignment of V and B versus Lorentz force was the connection that I wanted to ask.
Well, I was just being loose in that, but we have that alignment.
J and B.
J
and B, okay. So helical.
Other questions, please? Yes. Hunter.
I missed the beginning. Do you include a nuclear fusion reaction all in your simulation, or it's provided by heat source?
Oh, well, we incorporate, since we know what the temperature and density structure is in these stars, we put in reaction rates that would be consistent with nuclear burning, in particularly the CNO cycle, a function of radius. So
right, but due to your dynamo or convection, the condition could be different, right? Is it different, or maybe it doesn't change that much?
It doesn't change that much.
Okay.
Well, I mean, the models that are built in order to have these stars have at least have to have some treatment of convection. It's a mixing type of treatment. So in these MESA stellar structure models,
means we're not affected. Oh, okay. Just want to check. Thank you.
Other questions, please? Yes.
So you showed that table where you had the ratio of magnetic to kinetic energy ratio?
Yes.
So what exactly is being changed as we look down the table?
Well,
is it a Rayleigh number? Are you increasing?
We're changing the rotation rate from something at the top of that table that was very slowly rotating to something that it was rotating at about 15 times that of the sun, or 16% of the breakout velocity at the surface. So very fast rotation. So it's really, here we were primarily only changing the rotation rate.
Okay. And is the Prandtl number held fixed?
Yeah.
Nu over kappa?
Yes.
Okay.
So all of these things are run with a Prandtl number of 1/4.
Oh, okay.
And a magnetic Prandtl number of 4.
Okay.
And the basically reasonably viscous by Peter's definition. We'd love to be otherwise.
Any other questions? Yes, please.
This is just a question about that same table. You had one experiment designated H4, which presumably had no magnetic field allowed.
Right.
And it had an enormous kinetic energy, which was bigger than the total energy of the nearby.
That's right. Well, so it's fairly interesting. These stars, if we said we believe in hydrodynamic stars, then they would have a substantial differential rotation with them. I went fast. Almost any dynamo action basically clobbers that. So the cores themselves become almost uniformly rotating. Small, very small variations. Yeah.
Okay, thanks very much, Yuri, for a very interesting talk. Let's resume at 11 o'clock.